There's two approaches to how people solve RC and RL circuit. There's the differential equation approach where you always use differential equations. I don't believe in that. I believe in trying to get as physical so that you understand what is going on in the circuit. So what you're going to see here is that we're going to solve a generic form of a first order differential equation for an RC and an RL circuit. And from that, what you're going to find here is that we're going to use this assuming that we always have a constant source. The problem is, we're not. Right at the end, we're going to look at time-dependent sources. And when the time-dependent sources come in, you'll see that it really plays a big role in how you solve the problem. So we're going to spend a lot of time on constant sources, and that's where you get your physical footage. Okay? Because I'm going to ask you, why is it charging up? Why is it discharging? Why is the inductor storing more current? Why is the inductor decaying its current? And you got to step back and you got to look at the circuit and go like, oh, this is what's happening. You got to intuitively understand, because once we hit the mathematics, we're in a race, okay? And that race leads to not really physically understanding what the circuit is doing. You got to pay attention, okay? You got to pay attention to physically, because if you get an answer that's screwy and you write it down and you know it's screwy, I'm going to dock you right away, right? You got to see where we're headed here. So here we go. So now we're going to look at the complete response of an RC and RL circuit. So what I verbally said here is that there's two types of circuits that we're going to be dealing with. Okay. We have an RC. So when I say C, this means that I could have multiple capacitors, but I have to be able to reduce all the capacitors into one irreducible value. So when we're talking about this, this is an irreducible value. That means I can't break it down anymore. The same thing with the inductor. I could have multiple inductors. But then what do I got to do? Inductors, how do we deal with inductors? Exactly the way we deal with resistors. We add them in series, we take the inverses when they're parallel. When we're talking about capacitors, if they're in series, then they act as inverses. Whereas, if they're in parallel, they add. So then we also just mentioned here that there are going to be two types of sources. One, we're going to have constant sources. And then the other one is going to be time dependent. And they're two different techniques. I could treat them exactly the same, but then you lose all contact physically with the circuit. You're so focused on deriving the differential equation every single time that you lose the essence of what the circuit is doing. So I'm going to try to ground you and build your intuition here. So when we go to here and we go to chapter 9, that you'll have that basis. So remember, this here is that you want to build intuition on RC, RL circuits. And you'll see that this guy here is just very mathematical and hard to see. So once we build this, you'll see that you'll be able to understand what's going on here. So again, there's two approaches that people who teach circuits, they just do all differential equations right from the start. And you're just practicing deriving, the differential equation from the circuit. So what you're going to find here is we're going to do this here. So when I look at the complete response of a constant source, you're going to find here that what we want to do here is that we're going to do the same thing all the time for constant sources. So what we're going to find here is that if I have an RC circuit, our number one goal is to convert into a Thevenin circuit. So no matter how complicated that circuit is, we always want to reduce it just to a plain RC circuit. So what I'm saying here is that I'm going to want a circuit that looks like this. So no matter how complicated this is, it's always going to be this circuit. Now note, we're not going to be able to do this with time-dependent equations. It turns out that it's easier to just go right after the circuit here. It's more time efficient. And then if I have an RL circuit, no matter how complicated it is, we want to convert it into what? Into a Norton circuit. And so that means here that I'm going to have a circuit that looks like this. I short circuit, I still have my Norton resistance, and then I'm going to have my inductor. And what's really nice about this thing here is that, it's very common that people sort of like apply voltages, KVL, going around the loop with an inductor. And you're going to see that a lot of textbooks actually get that wrong. I mean, if you look at like Halliday, Resnick, and Walker, the book that you guys used for 4B, what he does in that book is absolutely wrong. Even our circuits book does it absolutely wrong. And maybe if we get into a circuit, I'll show you what I mean here. Because when you have you gotta include the inductance of the loop. And the only way you can do the inductance of the loop is that you have to do a line integral of the electric field all the way around that loop. Because a lot of times, as we'll find out here, people say, wait, there's a minus sign. There is. But if you use voltage divider rule, KVL, that minus sign sort of like is hidden. And you'll see what I mean. There's some technical issues. So what I want to do here is that I'm just going to pick an easy RC circuit. So I'm going to start off with the RC circuit, and I'm just going to go through the process with you. Right? And we kind of did this circuit that I have. We did this when we were doing PSpice. And so I, again, want to look at that circuit and just to physically show you what it was that we did here. So what we had is that you had a circuit like this. Actually, let me put another resistor. So what we have here is we have R1, R2, R3, we have C, and then I'm going to set up a switch right there. And when I set up the switch, I'm going to put my ground down here at the bottom. So when I set up this switch, what you're going to see here is that this switch closes at t equal to 0. And one of the things that we said here is that when we have a circuit like this, what we're most interested in is always calculating the voltage of this capacitor as a function of time. And just like mathematically, as we've talked about already here, this requires a first-order differential equation. Why does it require a first-order differential equation? Because the capacitor is not a linear element. It depends on time. So if I integrate the capacitor equation, or I write the capacitor equation in this language here, you'll see that I'll be able to either derive a differential equation or you have an integral equation. And as a consequence, you end up with an initial condition. So there are a couple things that we want to think about here. So what we want to do here is that when we analyze when we say the complete response of the capacitor, what we typically mean here is that we're going from 0 less than t to 5 tau. And we assume here that at 5 tau, it's at steady state. Or it's very, very close to steady state. And it's not changing very much. And so there's these sort of like intervals that we'll look at. So this is what we're primarily interested in. So if I start to sort of like look at the behavior of this thing here, so what happens here is that I need a Thevenin circuit here. And if I have a Thevenin circuit, I'm after this guy right here. So you can see here that I'm going to go through a series of steps here. So there are 3 distinct time periods. So the first one that I would call here, I would say when t is less than 0. So you gotta be careful with this language. What I really mean by this is that it's minus infinity, less than t, less than 0. That means that the capacitor has had plenty of time to completely charge up. So this implies here that the cap fully charges up. And what you're going to find here is that when you look at the circuit here, you can see right away here that when I calculate this thing and I put 0 minus, that means this value right there. So the very first value that we're getting right here is we're getting what is called the initial condition on the cap. So then the second period is that the switch is thrown. And when you see this switch that's being thrown, note that it's now a different circuit. It may look similar, but it's a different circuit. And because it's a different circuit, we treat it differently. And so what we're looking at now is we're looking at this time. And this time is what we typically call the transient behavior of the cap. And this is what we're most interested in. And so what happens here is that this period here is now the switch is thrown and the circuit is converted into a Thevenin. Okay? And then that's the equation that we actually go after and solve. And so how do we typically write this? So when we say that we're saying that we're in this period That, by definition, is the voltage of the capacitor as a function of time. This is what we're most interested in. But it turns out that to get this solution, we need this initial condition for the circuit, right? A first-order differential equation requires one constant, and that's the one. And then the next circuit that comes into play here is that just by looking at the circuit here, as t goes to infinity, what is the voltage of that cap? It has to be the Thevenin voltage. So then what we're finding here is that then there's, now I'm going from to t equals infinity, which means that it's in its final steady state. And we could see that at t equal to infinity, this must be the Thevenin voltage. Okay, it must be the Thevenin voltage. So if I was to physically look at what is going on here, if I was to just plot, what we're seeing here is that if I look at the voltage of the capacitor here, and this is my time axis, what you're seeing here is that this guy comes in. What does it come at? It comes in like this. Then there's a switch that's thrown. So if I look at this switch here, what happens here? I have 3 resistors. So if these are 3 resistors, you can see that when I throw the switch, I have a smaller resistance. A smaller resistance overall means that there's more current here, so therefore the capacitor has to have gone to a higher voltage. Now it could have discharged, and you'll see we'll go over those details later, but what you're seeing here is that there's a cap on this circuit here. If that's the Thevenin voltage, you can see that the capacitor must be at this point right here. So how I get from this initial state to that final state is this guy right here. And so what you'll see here is that this is the guy that we call VC of t. This is what we're most interested in. But you're going to see that where the fun stuff happens is actually right here. Because when you start to look at that circuit, even though we already know that the voltage before and afterwards are the same, we'll start to look at resistors and other things that are in the circuit, and you'll get all these cool discontinuities. And I think it's really fun because you get to really see how complex these circuits can actually be here. Now, in all fairness, there probably is we should probably talk about that there's a 4th circuit. What is this 4th circuit? Dude, you got to go back and solve the circuit problem. Maybe the circuit problem is this guy right here. Maybe you want this current, I2, as a function of t. Well, guess what? You got to go back to simple circuits. How am I going to get that? Well, I would get that current by doing what? I would apply KCL at that node. I know that current. Why do I know that current? Because it's parallel to VC, and I just calculated VC. I know this current because I calculated VC, and I know if I take the derivative of VC, I get the current of IC. So therefore, this current must be the sum of these two right here. But where everything relies now is this guy. So what you got to do here is that now you have to solve the circuit problem once VC of t is determined. So let's kind of count, right? Let's kind of count. Well, one circuit is definite to the initial condition, that's one. When I get to here, I at least have 2 circuits, right? Because to get 2 circuits means I got to get the open, and then I got to get RTH. So whether I write a short, or if I set, the source is equal to 0, depends on what we'll do here, but we'll remove this load. And so when I remove this load, I've got to look at what do the resistors look like in the circuit. So I would say there's 1, 2, 3, 4. So check this out. You got 4 circuits to solve this problem right here. So you can see that you're going to get a lot of stacking and you got of information here, man. And you got to get it straight, right? You can't be messing with this guy and mixing it up with that guy, right? You can't do that. You got to pay attention. And here's where all that node training, all that mesh training is going to be helpful, because by this point you better be really well organized in how you do things. Okay, so ultimately, what you're going to find here is that you're going to get something like this here. So if I was to write this as a summary, what we find here is that we call VC of t the complete response. Why do we call it the complete response? It's a complete response to this constant source. How does it respond? When I say complete, that means I'm talking about its initial condition, and I'm talking about its Thevenins here. And so if I was to sort of like break this all up to pieces here, at 0 minus, I would call this the initial condition. And then I get this guy here, which is the transient behavior. And then I get VC of infinity, which then gives me VTH, which is its final steady state. And you'll see in lab that if I set my square wave to be long enough, it'll reach that value. But you'll see that we really won't do that, because we're just going to go after 5 tau. And 5 tau means that it doesn't fully charge. It's very close, but not fully charged here. And what you're going to find here is that we're going to write down an equation, and it looks like this. So the complete response here is then reads as VOC plus VC of 0 minus VOC times e to the minus t over RC of this guy. And so that, like I said, is the complete response. What is this? This is what it's forced. This is the so-called forced response. What do I mean by the forced response? This circuit is doing what? It's forcing the capacitor to what voltage? That Thevenin voltage. That VOC value. And then what you're going to find here, that this guy here is sort of what they call the natural response. And what do I mean by the natural response? Well, this guy started off at this voltage, but the circuit is forcing it to that voltage. So it depends on how big of a step there is from the initial condition to its final steady state value. And that exponential essentially says, how do I move from this initial value? How quickly do I decay from my initial value to its final value? So that's effectively where we're headed. This is the solution we will derive here. Okay? And this is where you got to master this guy. And I think what's really nice about this equation here, by the way, we'll derive this thing. It's not that hard. But what you're finding here is that I think this is a very intuitive way of looking at it. Because then, when we go to look at the circuit, we're going to say, well, yeah, of course it did that. Yeah, of course it did that as it goes from this state to that state.